That's okay. So um, first, like just going over stuff you saw on Tuesday. So first, kind of basic idea.
Oh, I think he got to malonic ester stuff.
Oh, okay.
Base synthesis.
Yeah. All right. I thought he got further, but that's good to know. Thank you. Right. So, yeah, basic idea, just going over like what a keto and an enol form is, and we're looking at acetone here. So, I'll start with the keto form, and this is acetone. It's propanone, but acetone is like a common name for it. Can anybody either draw or describe the enol form of this structure? Like, what does it have in terms of functional groups? If this has a carbonyl, it's like a double bond to oxygen. So, yeah, and alcohol, and what else? That's where the OL part, and yeah, with a carbon-carbon double bond. So it should look something like this. Because it has an alkene, so that's where the ene part of enol comes from. And then it has an alcohol, so that's where the OL part of enol comes from. So if that helps you remember, then just think about that. The functional groups explain the name of it. And there's like an equilibrium between these two structures. So like it can be one or the other, kind of depends on what you have added to it. But like with nothing added to it in nature, one of these is more stable and you're going to see more of it than the other.
It's the
Which one?
keto form.
Yeah, the keto form. So for basically every structure, the keto form is going to be heavily favored over the enol form. Like I don't know the exact number. I'm kind of just going to make something up. But like for the enol, it's going to be something really, really small like this. Like I'm not saying to memorize this number. I don't know if that's even correct. Just like it's a really small number. It's close to zero. It's not exactly zero, but it's very close. So the keto form is like there's a lot more of it. So you have to do stuff to push the equilibrium towards the enol, basically. And if there's any questions about number one, feel free to ask. But number two is asking what Tautomers are. Like these two, a keto and an enol, are Tautomers of each other. And how could we describe them out of those four options? I'll actually, unless somebody answers before I put this, you can go ahead and put what you think here. It was in the slides, so you can always just refer to that or remember from there, but it should make sense too. I'll wait like 10 or so more seconds. Okay, I'll end it here. I don't have many more things I'm gonna pull on today, but like for future reference, I know I've said this before, but like um, I don't use the polls to like grade participation or anything. I'm more doing it to like get an idea of how you guys are doing in the class. Like if a bunch of people put the wrong answer, then I know to explain why it's wrong and why the correct answer is what it is in more detail. But if I don't know, then I won't explain it. So don't just put something random, like always try to put what you're thinking so I can tell how you're feeling, just for future reference. But the majority of you said C for constitutional isomers, and that's correct. They're not resonance forms because resonance forms usually push like electrons around, like it pushes a lone pair and a positive or a negative charge around, and it will have the same bonding pattern. So like they have all of the same atoms in the same spots. And like with the keto and enol form, like we're basically moving this hydrogen that I drew in from that carbon to the oxygen up here. So that's not the same bonding pattern because you moved the hydrogen. And then these two, diastereomers and enantiomers, are those are stereoisomers. So that would be something like if you have dashes and wedges and like different alkenes and you're looking at like different stereochemistries, that's what you would be looking for to use those two terms. And those also need to have the same bonding pattern. I guess that's another thing that kind of rules them out. But on top of that, like we're not really looking at any different stereochemistries, so that kind of rules them out. And constitutional isomers are, like, they have the same chemical formula, but different bonding patterns. Which is what this is. Like we just moved the hydrogen, so we have a different bonding pattern, but it's the same number of carbons, hydrogens, and oxygens. So it's the same formula. So just know that's what a tautomer is, and keto and enol are tautomers of each other. And there's also a true false here. The more substituted an alkene is, the less stable it is. This is review, but it's been a while since we've talked about it. So just kind of checking up on this. Okay, that was pretty fast. And you're all correct. So yeah, I won't go into much detail on this. Just this is false. More substituted means more stable. I don't think you have to know why, just this is a fact that you should be aware of, but it seems like you all are, so that's good. Okay, so I'm gonna go ahead and erase the screen and go to the next one. So kind of have been talking about it more in class now, but like for the next two chapters, we're gonna be looking at alpha and beta, like reactions that affects those two positions a lot. So it's good to be able to like identify at a glance what's alpha and what is beta. And in this class, it's always going to be like you're looking at what's alpha and beta to the carbonyl. So like you're looking specifically at like this carbonyl carbon or this carbonyl carbon or this one. Like that's what you're focusing on, what's alpha to that carbon that I have circled in all these structures. And in general, like, how could you describe an alpha position? Like, if this is carbon 1, the carbonyl carbon, where is alpha relative to that?
Alpha is the carbon that's right next to the carbonyl carbon.
Yeah,
Like there's
so
nothing in between, it's the first step.
yeah, and you could kind of call that like a 1-2 relationship to sort of generalize it. if you're starting with the carbonyl. And this is an alpha symbol. That's how I draw it, just so you know. And if alpha is a 1, 2, so like this would be alpha in this structure. It's right next to the carbonyl on carbon 2. What should beta be? Yeah, it's the next one over, the one free. The carbonyl. So it'd be this one in this structure, because that's like carbon free relative to the aldehyde. And it'll be the same idea with any other structure you ever look at. Alpha is just right next to the carbonyl carbon. Beta is 2 carbons away from the carbonyl carbon. So it's like a 1-free relationship. And like I say in the question, you can have multiple alpha or beta positions. So you might see that. So like here, unless you guys draw on it, it'll be hard to like show me. So I'll just kind of go over it. But like this is still carbon 1. You can call both of these like 2 relative to that. We're not numbering it like how we would name it. I'm just kind of numbering it to describe alpha and beta. So those 2 are right next to it. And then all of these positions are like 2 carbons away from the carbonyl carbon. So you could say those are all beta, and then the ones with the 2s are alpha. So those are all of the alpha and beta spots, and I'll erase the numbers to make it a little more clear. But yeah, that is basically the idea. You can have multiple, just if it's right next to the carbonyl, it's alpha, 2 carbons away, beta. Gets kind of repetitive after a while. If this doesn't make sense to anybody though, like feel free to ask. I'll clarify anything you need me to, because you're going to be doing this a lot. So if it doesn't make sense, like please ask. But it's always the same idea. Just 1 carbon away from carbonyl carbon is alpha, 2 away is beta, and there can be multiple spots. So I'm assuming there aren't any questions. If there are, again, please ask. But I'll go ahead and move on.
Alpha beta only refers to carbons, right? So like we wouldn't count the hydrogen or the OET.
Well, theoretically, it can refer to other things, but in this class, yeah, it's only going to be carbons. So like you could say like this ester part is also alpha to the carbonyl, and you could say the oxygen is alpha, but you don't have to worry about using it in that way in the class. For the purpose of the reactions, it'll always be carbons. So good question. And if you happen to be like in some sort of chemistry major, you're going to take 113B at some point, you might have to like use these alpha beta designations more then, but for now, you don't have to worry about it beyond looking at carbons. Okay. So I think you've talked about this more in class at this point. So this will kind of just be reviewing what you saw there, but this is an enolate. You have a negative carbon, and that carbon is alpha to a carbonyl carbon. So this is an enolate. And there are some ideas that you've seen in the past that you can use to explain the relative base strength of this base. And then from that, you can kind of say something about the strength of the acid. Because strong bases like have weak conjugate acids and weak bases have strong acids. That's a general idea you've seen before. So yeah, we can consider things that might affect the strength of this base. And what's one big thing that we can talk about with this enolate that will affect its like stability, reactivity, like how strong it is? We have a lone pair. Oh, go ahead.
I was going to say the negative or the lone pair.
Yeah, but what about it? Like, I have a hint here. Like, typically, if you're not sure how to explain something, resonance or induction are two factors that you can usually fall back on.
This
So,
one might be weaker because it has a resonance form and it can be stabilized.
yeah, the lone pair right next to a double bond, you can show a resonance form by pushing it towards the double bond. And then this is like a concept from 112A that like the more resonance forms a structure has, the more stable it is. So that's what you were getting at, which is correct. Forms stable. And if something is more stable, what does that say about its reactivity? Well, I think you already said it, actually. And if we're saying the base is less reactive, then it's a weaker base. So that's kind of the thought process you should have if you're trying to explain this. The resonance means the structure is more stable, so it's less reactive, so it's weaker. And because it came from, like, because this base is relatively weak, because of all of that, its conjugate acid is relatively strong. And the conjugate acid is just a ketone, like just a regular ketone like this. This was like an acidic proton that we took away to form that base. And that's a relatively acidic proton because of all of that stuff we just talked about with the base making it weak. And I think I'm assuming you saw, like, there's a slide in a lecture and there's a page in the book that has like a table of pK values. You've seen that like pKs for hydrogens like this, I think they're around like 20. Like, it's not super low, but it's much lower than 50, which is what you would expect for a hydrogen on a carbon. So this is a relatively strong acid. And yeah, that's just like a big part of the reactions in the next two chapters, the facts that you can take these hydrogens. So good to be able to rationalize why you can do that. A lot of this is like ideas we've seen in the past, but are there any questions about any of this before I move on? I don't know if he would ask a question exactly like this, but he could ask you to rationalize why enolates are weak bases, so the acid is relatively strong. Because he likes to ask questions where you have to explain stuff. I'll just move on unless there's a question. So you can show the mechanism for tautomerization, going from a ketone or an aldehyde to the enol form. And it can happen under acidic or basic conditions, so you should be able to show both. Can anybody tell me what the first step for the acid catalyzed tautomerization should be?
Movement of the double bond
Towards what if we're moving it?
towards the middle.
So like this?
Yeah.
I don't think you will. I don't think you could do that like as a resonance form if that's what you're thinking, because we would need to have like a positive charge here already to move the double bond like that. But we can do something to the structure to kind of make it so we can end up forming a double bond here to stabilize something else. What do we typically do? Like, it's actually, yeah, it's going to be the same thing we normally do with acid catalysts when we have carbonyls. It's going to protonate the carbonyl oxygen. And just as a general note, like to kind of help with mechanism approaches in general, if you're ever not sure about how to start, and like that's okay to be unsure, but like a lot of the time, one of the reagents you're adding, like the first step of the mechanism should involve a reagent you're adding. It should either attack something with electrons or be attacked like we're doing here. Because it like you're either adding a catalyst to promote it or it's just going to react straight away. So yeah, that's happening here. And what can we show with this structure that we have shown in the past?
Resonance.
Show resonance. And then we get a carbocation and we have our alcohol, which we want at the end, but we don't have a double bond. How can we form that double bond? In that first step where we took a hydrogen from the acid, we ended up forming A minus. So like if it was HCl, this would be Cl minus, just whatever the acid was. You have the conjugate base. So this can act as a base. It can take a proton and it can do something that's kind of like an E1 mechanism. It's not exactly E1, but it's kind of similar because we have a positive charge and we're taking a neighboring proton to take or to form a double bond. And then at the same time, you're gonna reform the acid catalyst. So the catalyst is regenerated at the end, which is good. That's the definition of a catalyst. It should be regenerated at the end. And that's the whole mechanism. And like up to this structure, this is the same kind of mechanism we've seen in the past for acid catalyzed mechanisms, protonating the oxygen, then drawing a resonance form. The only difference was like we did a sort of E1 mechanism here, but that's also something you've seen in a different context before, so it's not too different. So in the event he asks about this mechanism, this is how you do it. I'm gonna have to erase the screen to make room for the next one. So if there's any questions about this, feel free to ask. Okay. How can we start this one for the mechanism? And I will say this doesn't actually start the same way we normally would do a base catalyzed mechanism. It's not going to attack here at the carbonyl carbon.
Would it take an H from the alpha position?
Yep, because we've kind of discussed this is a relatively acidic proton and we're adding a base. So it's like kind of logical. Like if you're adding acid, it's going to add where there's electrons. That's why it added up here. If you're adding a base, it's going to take the acidic proton, which is this one. That's the most acidic proton here. And then it's going to form that enolate that we showed before. And what can we do with this negative charge to kind of move towards the enol form? It's actually something we've already done, like in a different question.
More resonance forms?
Push it towards the carbonyl oxygen. And then we form an alkoxide. And like we didn't, never mind. We have a negative charge. You never want to end with a negative charge, and we want an alcohol at the end. So this is where the protonated base that we used at the beginning comes in. It formed like HB, the conjugate acid. We have a base here, so just going to give the proton to the oxygen. And then that will reform the base catalyst, just like we reformed the acid catalyst. So this is a different kind of mechanism. It's not really similar to stuff you've seen before, but it hopefully makes sense because this is an acidic proton. The resonance form makes sense to go towards the enol, and then you have to protonate. And one other thing that I didn't really explain, but you might be aware of already. These ketones, like we could have potentially formed two different enols from them. I drew these ones as the products, but like we also could have shown this with the double bond going towards the left instead of the right. But what I drew is the major product. Like that's what you're going to see more of if you did this in a lab. And why would that be the case? Like this is something we can rationalize. Yeah, the one I drew is more substituted, so it's a more stable alkene. Because the alkene is what you're looking at. The alcohol is the same in both of them. It's like on the one I drew, it's a disubstituted alkene because it has those two carbons I highlighted in blue attached. And then for the one in red I drew down here, it just has this chain, so it's mono-substituted, so it's less substituted. Or substituted. Stable, I said. So this is just something to keep an eye out for. If you ever have a structure like this, it's always going to form the more substituted alkene. So that's where the enol is going to form. And it's because of the stability.
For both acid and base.
If he talks about it, there are some conditions you can use that I think will affect, like if it forms the more stable, the more substituted or not. But I think he cut it out last semester. So unless he says otherwise, assume it's always going to be the more stable substituted one. I can't say until he talks about it in class if you have to worry about it. But yeah, unless he says otherwise, just assume it'll be like this. And that's a good question, because I think the book will touch on it. So it might have been where that idea came from. Okay, this is another thing you have probably seen in class now, so you're more aware of the idea. But like, there's multiple different protons here, and one of them is going to be more acidic than the others. And we can kind of simplify this one a bit because these two, circled in blue, they're basically the same because they're just alpha to 1 ketone. And then the one in the middle is different because it has 2 ketones next to it. So we basically just have to consider 2 protons. When you're trying, well, like you can point to pK values, but if you were asked to explain this on a test, you can't just say the pK value for this proton is lower than this one, so that makes it stronger. You have to explain it somehow. And the best way to do that is looking at the conjugate base, where you take the hydrogen away. So this is the conjugate base if you took that blue hydrogen on the left away. And just like before, like we can kind of talk about its stability and reactivity by showing this resonance form with the carbonyl. We have this resonance form, and then like we can do similar stuff by showing the conjugate base for the proton I circled in red. We can show it going towards the carbonyl on the left, just like we did with the conjugate base of the blue one that I showed. But then we can do a bit more with this structure, because this negative charge, this where the proton was, like it's alpha to both of the carbonyls, not just this one on the left. So we can show another resonance form. So the one in red has 3 resonance, and the one in blue has 2 resonance. And kind of discussed this earlier, the more resonance forms a structure has, the more stable it is. So the red one is more stable because it has more resonance forms. it's a weaker base, which means the acid was stronger than the other one. So this is the most acidic proton because the base from that one is weaker than the other two. And you will have to know like the pK value for this. If it's a proton between two carbonyls, I think it's around 10. I could be misremembering, like I'll talk about it in more detail on the next worksheet, but I think it's around 10 or 15. It's relatively low, but in general, like even if you don't have a pK value for a specific structure, basically the more carbonyls that are alpha to a carbon, acidic hydrogens are. And that has the same reasoning we're going over here. If there's more carbonyls alpha, it's going to have more resonance forms for the base. So the acid should be stronger. So just as a kind of random example, if you had a structure like this, then this carbon here, like it's alpha to all three of these ketones. So it would be even more acidic than this one we were looking at that's alpha to 2 ketones. And you can't have 4 carbonyls alpha to it. Well, yeah, you couldn't have 4 because then you wouldn't have a hydrogen. So that's like as far as it could go, I guess, but it's just extending the idea a bit. Okay. I'll go ahead and erase this and move on to the next one. If there are any questions, tell me, go back, because this is another thing to be aware of. Like, you can just memorize this idea, that's perfectly fine, but also try to be aware of the resonance explanation, because if he asks you to explain it and you don't use the resonance explanation, he might not like that. So here we have a ketone and we're adding bromine and CH3COOH. What is the purpose of this bottom reagent, the CH3COOH? Like, what is that probably acting as? So it has COOH, that's a carboxylic acid. This is what it looks like. And like in this chapter, we're looking at reactions with enols and enolates. Remember a few minutes ago, we were talking about like the mechanism for making an enol. You could do it with acidic or basic conditions. This is an acid, so it can be that acid catalyst. This is like the HA from that mechanism we did earlier. So the acid you use could be basically any strong acid. Just any strong acid could be a catalyst, and that can help you form an enol. So I won't show the mechanism, but like that's the purpose of the acid. It's going to help us form this enol intermediate. And enols have alkenes. And you might remember from 112a that alkenes can act as nucleophiles. And enols are also going to act as nucleophiles because they have alkenes. This can attack electrophiles as a nucleophile. And you also might remember from 112a that Br2 could be an electrophile. We added it to alkenes before. So that's going to be the reaction happening here. And then after a little bit of rearrangement, and I don't think you have to worry too much about it, but that's like the general idea. The enol is a nucleophile. It attacks the bromine. In the end, you're going to have your carbonyl, and you would have added a bromine to the alpha position because of that nucleophile electrophile reaction. And this is just an halogenation. Not a very special or hard to remember name, but that's what's happening. We just added a halogen to the alpha spot. And the rest of the reactions are gonna follow the same kinds of ideas. So if there's any questions about this, now is a good time to ask, but if they come up later, it's okay too. Just if this makes sense, the rest will hopefully make sense too. If it doesn't, it's a good time to clarify. Okay, I'll go ahead and move on. Here we have an aldehyde, and we're adding chlorine and H2SO4. So chlorine is just like Br2. It's just another electrophile. What is this going to act as?
Nucleophile?
Not a nucleophile. Yeah, catalyst. It's going to help drive the enol formation because it's an acid catalyst. A base, yeah, it's okay. A base will typically have either a counter ion like Na, sodium, or potassium, or maybe he would just show you like OH minus or whatever, but usually it will have a counter ion. And then this is just another strong acid. But to help you distinguish between the two, if you see Na or K as a part of a reagent, that's usually either a nucleophile or an electrophile, or a nucleophile or a base. It's not going to be an electrophile. So yeah, that can be a clue as to what a reagent's going to behave as. So this is going to perform the same function as the carboxylic acid from the last question. It's just going to drive enol formation. And then the enol will act as our nucleophile, and it will attack the chlorine the same way the enol attacked the bromine before. And in the end, I'm going to have an aldehyde, and we add a chlorine to the alpha spot. So same idea, just alpha halogenation. This next one is a little different. The end product is going to be basically the same, but the conditions you use have to be like this because it's a carboxylic acid. And I don't know if you have to know all of these details, but I'm going to go over the details of this reaction, and that might help you remember what the end product is. So first, we're adding PBr3. Like there's also Br2 there, but we'll ignore that for a minute. what happens if you add PBr3 to a carboxylic acid? What kind of product should that make? This is a reaction from chapter 21 with the carboxylic acids and their derivatives. Yeah, it replaces the OH with a bromine to make an acid bromide. That's just the PBr3 part. And you don't have to know the mechanism for this transformation. So like you might just want to take note of and memorize this idea to help you remember. But as a byproduct of this, like you're gonna form HBr. That's a byproduct of this reaction. And HBr is another strong acid. It can be a catalyst. Enols formation. Just like H2SO4 was and the carboxylic acid was, those were also strong acids. They did the same thing. So that's what the HBr here is gonna do. So we get this enol. And then the enol can react the same way it did before with the Br2. The enol is a nucleophile, bromine is an electrophile. So that will put a bromine on the alpha spot. And then in the second step, we add water. What should happen to this structure when we add water to it? What happens if you add water to an acid bromide? What kind of product do you make? Yeah, it goes back to a carboxylic acid because that's a
Wait,
hydrol.
how does the oxygen get removed? I mean, how does the hydrogen get removed
Which hydrogen?
from the OH to an O?
Like this one to here?
Yeah, unless that
Uh,
was
Um,
something else.
I honestly don't think he will ask you about that mechanism, but I think it's in the book and the slides. It like after this attack of adding the nucleophile, there's not enough space here. I'll draw it over here. I don't think I'll show like a whole mechanism because I don't have it memorized myself, but you'd get an intermediate like this. Well, actually, I think it makes a decent amount of sense now that I'm looking at it. You could draw a resonance form after you added the bromine there, pushing the lone pair from the oxygen towards the positive charge. And then you could deprotonate this OH on the carbonyl, and then you get the carbonyl back. So that's how you could show that transformation. I just kind of skipped it. Does that make sense though? Like then, I guess Br minus, take that. Get back. So yeah, that's how you do that. And then it's not a lot of space either. carboxylic acid, because that's hydrolysis, that's chapter 21 reaction. So in the end, all we did is we put a bromine on the alpha spot. We have the same carboxylic acid. We just put a bromine at the alpha position. But like it goes through all these intermediates. You form the acid bromide, and at the same time you form your acid catalyst that helps you form an enol, so that can react with the Br2. And then the water is just doing hydrolysis to go back to the carboxylic acid. Like all of that is what's happening. And there's a name for this reaction where like these specific conditions with a carboxylic acid. And like most named reactions, it's good to know. So does anybody happen to remember what it's called? Not, it's okay. Can just take note of it. Yeah, it like that's like an abbreviation for it, and it's called the Helvohard-Zielinski. I might spell it wrong, but it's something like this: Helvohard-Zielinski HVK reaction. So yeah, know the name, the conditions, and I honestly don't know if you have to know all of these intermediates, but it definitely helps remember what's happening. Otherwise, it's straight memorization of the conditions and product. Okay, here we have a ketone and we're adding IO2 and acetic acid. And I'll just say acetic acid, in case you weren't sure, is this, which is the same carboxylic acid we were working with before. It's a pretty common acid catalyst. It's just being named instead of drawn like before. So it's going to do the same thing it did before. It's going to help us form an enol. But what enol are we going to form here? Like there's two potential ones. Form this one.
Form the more substituted one.
Yeah, so the one on the right. So this is going to be the one that forms faster because it's more stable. So that's going to be the one that we use for our reaction. And then the bromine is going to add here because we're using that, or not the bromine, the iodine. The iodine will add there because that's the enol that we're going to be using to react. So this is the product you get. Next one, we have carbonyl, and we have a bromine, and we're adding pyridine to it. What can pyridine behave as? I'll go ahead and draw it, but you can also tell me before I finish drawing. Looks like this. Yep, it can be a base. And if we add a base like this to a structure like this, I suppose it could do multiple things, but what's one thing it can do? Like considering we have this bromine here, what kind of reaction can happen?
Acid-base reaction.
Yeah, but specifically, like we have a hydrogen here and we have a bromine here, which can act as a leaving group. So we can do an E2 elimination. So like this is an acid-base reaction, just it's also an elimination because of the halogen there. And the base doesn't have to be pyridine, it could be any other base. But just adding a base to a structure like this can make an alkene. And I'm kind of just reiterating what Okuda said in class, but you've seen structures like this in the past with an alkene on the alpha and beta spots to a carbonyl. And remember, like we had special reactions with structures like this because they had this resonance form. Puts a positive charge on that beta carbon. And so most nucleophiles will attack there. That's just something we've seen in the past. And just kind of emphasizing like that's the product of this reaction. This elimination gave us this conjugated ketone with the alkene that you can do more reactions with.
So the first one you drew is the product because there's nothing else in here with the pyridine?
Yeah, if you mean like, if I had a nucleophile or something, it could do a different reaction. Like maybe it would do an SN2 here, but the pyridine by itself is just going to be a base and do this E2 reaction.
Okay.
Good question. So yeah, different conditions could do different things. And I also just want to highlight, like, if you didn't recognize it, this structure we started with, like, it just has a bromine on the alpha spot. All the reactions we've been doing today make something like this as a product. So this is just a product of these alpha halogenations. And then if you do an E2, you get a structure like this. And then when you have a structure like this, you can do more reactions because you've seen this before. You've done plenty of reactions with these conjugated ketones. So this is something that could come up in a synthesis problem on a test, maybe, just like this is a way to link reactions from a bunch of different parts of the class. Because E2 is 112A, we're using reactions in this chapter to make this kind of product. And then a few chapters ago, we did stuff with this. So like, it is a thing that could come up on a test. I'm not saying it will, just it could. So it's a good thing to understand. Okay, here we have a ketone and we're adding bromine and acetic acid again. So we're going to be doing an alpha halogenation like we have been all day. But since we have a ketone, like we have two different spots the bromine could go to, is it going to add here or here on the left or the right?
The left,
Yeah, and why is that the case?
because the right carbon is already fully substituted.
So even though the right is more substituted, it's too substituted. We can't form an enol there, so we can't add the bromine there. So something like this is basically the only exception to like you always form the more substituted halogen. In this case, you can't put it on the more substituted side, so it doesn't go there. And if you want to generalize this, like this is a quaternary carbon, so basically like if you see a quaternary carbon or if there's no hydrogens around, then you can't put something there. You need at least one hydrogen to form the enol to do this reaction. This next one is fairly similar to the Helvohard-Zelinsky reaction. It's just the second step has NH3 and triethylamine instead of water. So I'm gonna like skip to the point where we have that intermediate with the acid bromide, and we've put a bromine on the alpha position. Like this is an intermediate. And then this is the part where the water came in before. But this time, like I said, we're adding NH3 instead of water. What is that going to do to the acid bromide? Like what happens if you add an amine in general to an acid bromide?
Make an amide.
Yeah, so I don't think this is something Akuda really talked about this semester, but instead of adding two equivalents, you can add one equivalent of an amine and then a base. That's what the triethylamine is for. It's like the second equivalent of amine, just to explain why it's there. So it's the same amide forming reaction as before. It's going to convert that bromide into an amide. So we're ending with an amide instead of a carboxylic acid, but it's the same kind of process. And I don't know if he would do something like this, but this is just sort of a mix up that like maybe he could do. He could put something else here too for a second step if he wanted. Like suppose he put like methanol for the second step instead of NH3. What would the product be if we put methanol there? Like what kind of functional group would we make if we're adding an alcohol?
An ester.
Yeah. So just saying like in general, maybe he could throw stuff like this at you. So don't forget about the old reactions. They could come up here. I'm gonna go ahead and move on to the last page. Watch the recording later. Okay, so here's a synthesis, and like usual, I think it's good to like take note of functional groups you're starting with, functional groups you end with, maybe if you added carbons, stuff like that. So starting with an alcohol, and then we converted the alcohol to a ketone. We also made an amide, or not an amide, an amine. So those are the changes we're making. And another good thing to take note of is like if you have an alcohol, what kind of alcohol it is, primary, secondary, or tertiary, because that will affect what kinds of reactions you can do with it. So the one we're starting with is secondary. So that's just good to take note of. That might affect what reactions we do, how we work with it. And then at this point in the class, like you're going to be doing a lot of reactions that have to do with like the alpha position and just like maybe beta too. Well, you'll start seeing that in chapter 23. So like it's good to consider like what the relationship is between functional groups in a product is. That might affect the synthetic approach you have. So like in this case, I'm pointing that out because the amine is on the beta position relative to the ketone. So that can affect the approach we use to make this product since it's at the beta spot. And this is one approach you could use for this. You could kind of work backwards from this. Remember earlier today, I pointed out how these structures, like you've seen it in the past, these alpha, beta, and saturated ketones have this resonance form. It puts a positive charge on the beta position, and then most nucleophiles will add to the beta position. Well, we have an amine, which can act as a nucleophile on the beta position to the ketone. So it would make sense, like if we're working backwards from the product, like if the immediate precursor to this was something like this with a alkene on the alpha and beta spots. Because then if we added an amine, it would add to the beta spot, we'd get that product we want. So then we could just add this amine and it'll add there, we get that product. So we know what the immediate precursor was. Just gonna erase that. Oh, didn't want to erase the whole thing. So like you can kind of work backwards, figure out that's what you need to make this. And this again, like might not jump out at you on a test. So like you can always work forwards from the starting point to try to meet yourself in the middle. But since we've been talking about it today and it was brought up like during lecture, something that might be an idea in your head is, well, I have a double bond like this. One way I could make that is if I started with a structure like this with a halogen on the alpha spot, and then you add a base to make that in an E2 reaction. So like we could add pyridine or any other base, doesn't really matter. Just some sort of base to do an E2 reaction to make that alkene. So that's another way that we can work backwards further. And this bromine is on the alpha position. And that's basically the whole thing we've been doing today, adding halogens to the alpha position. So we can continue to work backwards to figure out what we had before that. We could have just had a ketone. And we added Br2 and some sort of acid. I'm going to put acetic acid, but it could be any other strong acid. It doesn't really matter. And then at this point, we can go from the alcohol to the ketone. And to do that, you would just want to oxidize it. And you can use any oxidizer. I'm going to put PCC just because if I was doing this on a test, I think that's the first thing that would come to mind, but you could pick any one that comes to mind. It doesn't matter for this. So that is the most direct approach for this synthesis that I could think of. There are probably other correct ways to do it. So if this isn't what you put, that doesn't mean you're wrong. I can check it if you'd like, as usual. But if not, that's okay. Hopefully this makes sense. And that is all I've got for this worksheet. So I'll stick around if you have any questions, but if not, we can end a few minutes early. It's okay with me. Mhm.
Yep. Thank you.
Have
See
a
you
good
next week.
weekend.
You too. Oh, actually, real quick. Hey, do you watch Marvel movies at all?
A little.
A little bit. Oh, okay. Have you seen like trailers for the new Eternals movie?
I've seen
Eternals?
trailers. Yeah.
Dope. All right. Well, if you do see it, we should totally talk about it. It'd be so cool.
Okay. If
All
I
right.
see it,
Yeah. Have a good weekend.
you too. Any last minute questions before I end the meeting? All right, I'm guessing you're not there. So have a good weekend. Yeah. See you next week.